Hello there, and welcome to the Sleepless Scientist, a quiet place where curiosity slows down, thoughts loosen their grip, and science becomes something soft enough to listen to as the day fades away. Tonight, our journey drifts into a subtle and often overlooked corner of science, a place where life itself may be quietly borrowing a few tricks from the deepest rules of reality. This story is about quantum biology, the idea that living organisms might be making use of quantum phenomena, not in laboratories or particle accelerators, but inside leaves, cells, and even the eyes of migrating birds. Before you settle in completely, you're welcome to like this video or subscribe if these calm explorations are something you enjoy returning to, and if you feel like it, you can leave a comment sharing where you're listening from and what time it is for you right now. It's always a gentle reminder that we're scattered across the world, each in our own small pocket of night. Now, take a moment to get comfortable. Maybe the lights are already dim. Maybe there's a soft background hum, rain, a fan, or distant traffic. And if your attention wanders at any point, that's perfectly fine. You don't need to hold on tightly to every idea. Let them pass through, like clouds moving slowly across a dark sky. Tonight's question is a simple one, though it leads somewhere unexpectedly deep. Is quantum mechanics really as strange as we've been told, or is it only strange to us? For many people, the very word quantum carries a certain tension. It brings to mind equations that refuse to behave, particles that seem undecided about where they are, and a world that does not follow the common sense rules we rely on every day. Even physicists, people who have devoted their lives to understanding nature, often speak about quantum mechanics with a mixture of admiration and discomfort. In the quantum world, things do not always have definite positions. Outcomes arrive as probabilities rather than certainties. Energy does not flow smoothly, but in small, discrete steps, and connections can exist between distant things in ways that seem to ignore space altogether. It's no wonder this makes people uneasy. We are creatures who like solid ground, clear causes, and predictable effects. But here is a quieter thought, one that rarely gets attention. Life itself has never been neat. From the very beginning, living systems have existed in a state of constant uncertainty. Cells are noisy places, crowded and chaotic. Molecules collide at random, signals overlap, processes interfere with one another. Nothing is perfectly isolated, and nothing is ever fully at rest. If you could shrink yourself down and wander through a single living cell, it would feel less like a carefully engineered machine and more like a bustling city at rush hour. And yet, life works. It adapts. It repairs itself. It survives mistakes. It even turns randomness into opportunity. Evolution, after all, is built on variation and chance. Living systems don't just tolerate unpredictability, they depend on it. So perhaps quantum mechanics feels strange not because it is incompatible with life, but because it clashes with a particular way of thinking we've grown comfortable with. A way of thinking shaped by clocks, gears, and straight lines. A way of imagining the universe as something that behaves like a well-organized machine. Biology never signed up for that model. Living systems have always operated in environments that are warm, wet, crowded, and restless. They do not wait for perfect conditions. They do not require silence or isolation. They function amid interference, fluctuation, and noise. In that sense, life may already be fluent in a kind of reality that physics once found unsettling. This is where quantum biology gently enters the conversation. Quantum biology does not claim that cells are performing complex calculations, or that organisms are consciously manipulating quantum laws. Instead, it asks a much more modest and much more interesting question. If the basic building blocks of life are atoms and atoms follow quantum rules, could some of those rules still be quietly influencing how life functions? not in dramatic science fiction ways, not with glowing effects or exotic powers, but subtly, briefly, and just long enough to matter. Imagine walking through a forest at night. You don't see every path clearly. Instead, your steps are guided by faint outlines, soft contrasts, and momentary hints of direction. You don't calculate every movement. You simply move in a way that feels efficient enough to keep going. Quantum biology suggests that something similar may be happening deep within living systems. Not precise control, but gentle exploitation. Not mastery, but cooperation with the underlying rules of nature. This idea can feel unsettling at first, especially if we've learned to associate quantum mechanics with extreme conditions, near absolute zero temperatures, carefully shielded laboratories, and fragile experiments that collapse at the slightest disturbance. Life seems like the opposite of that world, and yet this contrast is exactly what makes the question so intriguing. What if quantum effects don't need to be preserved forever? What if they only need to last for a fleeting moment, long enough to nudge a process in the right direction? Over billions of years, even the smallest advantage can shape the trajectory of life. A slightly faster reaction, a slightly more efficient transfer of energy, a slightly better sense of direction. These are not dramatic improvements, but evolution does not require drama. It requires persistence. So tonight, as we begin this exploration, you don't need to decide whether quantum biology is fully proven or where its limits truly lie. You only need to hold one gentle possibility in mind, that the strange rules governing the smallest pieces of reality may not be strangers to life at all. They may have been quietly present, guiding processes just beneath our awareness all along. And with that thought resting softly in the background, we can begin to drift deeper, toward the idea that what feels weird to us might simply be nature behaving as it always has. If we pause for a moment and look closely at how life actually functions, a quiet pattern begins to emerge. Living systems do not wait for clarity before acting. They do not pause until every variable is measured, every pathway mapped, every outcome predicted. Instead, they move forward amid uncertainty, adjusting as they go, responding to what happens rather than insisting on what should happen. This is not a flaw in biology. It is one of its deepest strengths. A single cell, for example, is not a peaceful place. It is crowded with molecules drifting, colliding, binding briefly, then separating again. Signals overlap, reactions compete, energy arrives in pulses rather than steady streams, and yet, somehow, order emerges, not because the chaos disappears, but because life has learned to work within it. In classical physics, especially as it developed in the age of clocks and engines, uncertainty was something to be eliminated. If you knew the position of an object and how fast it was moving, you could predict where it would be next. The universe, in this view, was like a finely tuned machine. Predictable, reversible, and calm. Biology never lived in that universe. Biology evolved in a world where conditions changed constantly. Temperatures fluctuated, resources appeared and vanished, environments shifted slowly, then suddenly. There were no stable reference frames, no perfectly isolated systems. Life did not wait for certainty. It adapted to ambiguity, and this difference in mindset matters. When physicists first encountered quantum mechanics, the discomfort came not only from the mathematics, but from the way it challenged deeply held expectations. Outcomes became probabilistic. Events could not always be traced back to a single clear cause. Some questions that felt perfectly reasonable, no longer had clean answers. But to a biologist, this landscape may feel oddly familiar. Evolution itself is not a precise process. It does not move toward a predefined goal. It explores possibilities, discards what fails, and keeps what works well enough to persist. It is, in many ways, a long conversation with uncertainty, not a battle against it, but a collaboration. Imagine a river flowing through a changing landscape. The water does not calculate the optimal path in advance. It spreads, explores, seeps into small channels, and gradually finds routes that carry it forward. When an obstacle appears, the river does not stop to analyze. It simply flows around, over, or through, reshaping the terrain as it goes. Life behaves in much the same way. This perspective invites a subtle but important shift. Instead of asking how living systems manage to tolerate uncertainty, we might ask how uncertainty helps them function at all. Randomness introduces variation. Variation fuels adaptation, and adaptation over vast spans of time gives rise to complexity that no single plan could design. From this point of view, quantum mechanics begins to look less like an intruder and more like a continuation of a theme. Quantum rules do not offer certainty, they offer likelihoods. They describe what can happen, not what must happen. For someone expecting the universe to behave like a clock, this feels unsettling. But for life, already fluent in probabilities, it may feel entirely natural. This does not mean that biology understands quantum mechanics, or that cells are somehow aware of the rules they follow. It simply means that life has always existed in a world where perfect predictability was never an option. In such a world, strategies that can make use of uncertainty, rather than being hindered by it, have an advantage. There is a quiet elegance in this idea. Instead of fighting randomness, life leans into it. Instead of demanding fixed outcomes, it accepts a range of possibilities and works within them. Instead of seeking absolute control, it develops resilience. And this brings us gently closer to the heart of quantum biology. If quantum effects introduce new ways for matter and energy to behave, ways that are not available in a purely classical picture, then even a small biological use of those behaviors could matter, not in dramatic leaps, but in subtle nudges. A reaction that proceeds a little faster, an energy transfer that wastes a little less, a signal that becomes just a bit more reliable in a noisy environment. Over millions of years, these nudges accumulate. It is also worth noticing that biology does not require quantum effects to last very long. Unlike engineered systems that aim to preserve delicate states for extended periods, living systems often operate on fleeting timescales. Moments that are almost unimaginably brief can still be biologically meaningful if they occur at the right place, at the right time. This is another way biology differs from our expectations. We tend to think in terms of permanence. If something matters, we assume it must last. But life often works through transitions rather than states, through changes rather than constants, a brief alignment, a temporary overlap, a momentary opening. These can be enough to influence the direction of a process. So when we hear that quantum effects are fragile, easily disturbed and short-lived, this does not automatically disqualify them from biology. It may simply place them in a category that biology already knows how to use. At this stage, there is no need to decide how far quantum biology ultimately reaches, whether it plays a central role or a supporting one, whether it appears in many biological processes or only a few special cases. What matters for now is the shift in perspective. Quantum mechanics stops being a strange set of rules imposed from outside life. Instead, it becomes part of the same uncertain, probabilistic, adaptive environment that life has always inhabited. The difference is not that biology suddenly became quantum. The difference is that we are beginning to notice how deeply quantum the world always was. With this thought in mind, we can continue our quiet journey, not by demanding clear answers, but by allowing possibilities to unfold gently, one at a time. As we drift a little deeper into this idea, it helps to pause and remember something very simple, something so familiar that it often slips past unnoticed. Everything alive is made of atoms. The air you breathe, the warmth in your hands, the quiet rhythm of your heartbeat, the slow turning of thoughts as you begin to relax, all of it arises from countless tiny pieces of matter interacting with one another. These atoms gather into molecules, molecules assemble into structures, structures organize into cells, and cells, working together, become life. This much feels intuitive, almost comforting. What feels less intuitive is what atoms themselves are like. Atoms are not solid little beads clicking together like parts in a machine. At their most fundamental level, they do not behave the way everyday objects behave. They do not always have precise locations. They do not move along clean, predictable paths. They follow rules that are, by their nature, probabilistic. In other words, atoms are quantum. This is not a metaphor. It is not an interpretation. It is simply how the smallest building blocks of matter behave. Quantum mechanics is not something added on top of reality. It is the framework reality already follows at that scale. And yet, for a long time, biology and quantum mechanics lived in separate mental compartments. Quantum mechanics was thought of as the domain of electrons, photons, and isolated experiments performed under carefully controlled conditions. Biology, on the other hand, was seen as a messy, large-scale phenomenon, too warm, too noisy, too complex for delicate quantum effects to survive. This division made sense historically. When atoms come together in large numbers, their collective behaviour often smooths out into something that looks classical. The unpredictability of individual particles averages away. The strange rules fade into the background. What remains is the solid, reliable world we experience every day. So for decades, it seemed reasonable to assume that quantum mechanics did its work quietly at the bottom, handing biology a set of stable chemical bonds and predictable reactions, then stepping aside. But quantum biology asks a more focused question. Not whether life is quantum at its foundation, that much is already true, but whether some distinctly quantum behaviours continue to play an active role once atoms assemble into living systems. This is an important distinction. Quantum biology is not simply another name for chemistry. All chemistry, at some level, depends on quantum mechanics. Without it, atoms would not bind, molecules would not form, and life would never begin. Quantum biology instead looks for situations where quantum behaviour does more than just set the stage, where it influences how biological processes function in real time, where it offers options that classical physics alone would not provide. You can think of it like this. Imagine a group of musicians playing together. The individual notes matter, but what truly shapes the music is how those notes interact, overlap, and resonate. Quantum biology is interested not just in the notes, but in the fleeting harmonies that emerge when they briefly align in special ways. These harmonies do not need to last long. They do not need to be perfectly preserved. They only need to exist long enough to influence what happens next. This perspective helps clear away a common misunderstanding. Quantum biology does not suggest that cells are performing complex calculations, or that life is secretly running something like a quantum computer. There are no internal processes, no error correction protocols, no sustained fragile states being carefully protected from the environment. Living systems do not aim for precision in the way machines do. They aim for usefulness. If a quantum effect offers a shortcut, a smoother transition, or a slightly more efficient pathway, even briefly, biology can take advantage of it, not deliberately, but through the slow, patient filtering of evolution. over vast spans of time, what works tends to remain. Another way to see this is to think about choice. In classical physics, systems often move along a single, well-defined path. Cause leads to effect. One step follows another. There is a sense of inevitability. Quantum systems, by contrast, can explore multiple possibilities before settling into an outcome, not by trying each option one after another, but by existing in a state that allows several possibilities to coexist for a short time. Quantum biology asks whether life ever makes use of this expanded menu of possibilities, not consciously, not dramatically, but quietly, at the molecular level, where even a tiny advantage can ripple outward into something meaningful. This idea also explains why quantum effects in biology do not need to be strong or long-lasting. They are not meant to dominate the system. They are meant to nudge it, to influence probabilities, not dictate outcomes. A brief alignment here, a momentary overlap there. Enough to tip the balance in favour of one pathway over another. From a human perspective, this can feel unsatisfying. We like clear mechanisms and durable explanations. We prefer systems that behave the same way every time, but life has never promised us that. Life operates in gradients, tendencies, and likelihoods. It works through patterns that are reliable, not because they are rigid, but because they are flexible. Quantum behaviour in this sense fits naturally into biology's existing toolkit. So when we say that life is made of atoms and atoms are quantum, we are not making a leap into abstraction. We're reminding ourselves that the strange rules of the microscopic world are not distant curiosities. They are present everywhere, all the time, quietly shaping the possibilities from which life emerges. With this foundation in place, we are ready to ask a deeper question, one that brings evolution into the picture. If quantum effects offer even the smallest functional advantage, why wouldn't life over billions of years learn to use them? When we talk about evolution, it is tempting to imagine dramatic leaps, sudden breakthroughs, radical transformations, moments when life takes a sharp turn towards something entirely new. But most of evolution does not move this way. It advances quietly, patiently, through differences so small they would be easy to overlook if we were watching in real time. Evolution is not impressed by perfection. It responds to advantage. A change does not need to be revolutionary to matter. It does not need a double efficiency or guarantee success. It only needs to make survival or reproduction slightly more likely than before. Over short timescales, such differences are almost invisible. Over millions or billions of years, they become decisive. Imagine a long-distance journey across uneven ground. If one path is only a fraction smoother than another, the difference may feel trivial after a few steps. But after thousands of miles, that small smoothness determines where the trail ultimately leads. Evolution works in much the same way. This perspective is essential when thinking about quantum biology. Quantum effects, when they appear in living systems, are not expected to create dramatic, unmistakable changes. They are subtle. They operate at the smallest scales. They influence probabilities rather than outcomes. And yet, this is exactly the scale at which evolution operates most effectively. A chemical reaction that happens slightly faster can matter. An energy transfer that loses a little less along the way can matter. A sensing mechanism that is just a bit more reliable in a noisy environment can matter. These are not changes we would easily notice, but they are changes evolution can work with. And evolution has a great deal of time. Life on Earth has been unfolding for billions of years. During that span, countless variations have been tested, discarded, refined, and reused. The vast majority left no trace. A few persisted, not because they were perfect, but because they worked well enough, consistently enough, to continue. quantum biology fits naturally into this framework. If a quantum effect offers even a modest functional benefit, something classical physics alone could not provide, there is no reason evolution would ignore it. Over time, structures and processes that accidentally take advantage of such effects would be preserved, while those that do not would quietly fade away. It's important to notice how unintentional this process is. Evolution does not seek out quantum effects. It does not recognize them as special or strange. It simply filters outcomes. Whatever contributes to success, regardless of the underlying mechanism, is more likely to remain. This makes quantum biology far less mysterious than it first appears. We're not imagining life deliberately manipulating the rules of physics. We are simply recognizing that life exists within those rules, and that some of them may be more useful than others under certain conditions. There is another aspect of evolutionary thinking that often goes unnoticed. Efficiency is not just about speed or strength. It is also about reliability. Living systems operate in environments full of disturbance. Temperatures fluctuate, signals degrade, resources vary. Under such conditions, processes that are slightly more robust, slightly better at finding their way despite interference, gain an advantage. Quantum effects in some contexts offer precisely this kind of robustness. By allowing systems to explore multiple possibilities briefly, they reduce the risk of becoming trapped in inefficient pathways. They do not guarantee success, but they improve the odds. Over evolutionary timescales, improving the odds is enough. It is also worth remembering that evolution does not optimize everything at once. It builds layer upon layer, reusing old solutions in new ways. What begins as a minor side effect can become a central feature if it proves useful. A structure that initially benefits from a quantum effect only occasionally may, over time, become better at supporting that effect. Not through foresight, but through incremental changes that preserve whatever works. This gradual shaping is slow, but it is relentless. Seen from this angle, quantum biology does not require a dramatic origin story. It does not need a moment when life suddenly became quantum. Instead, it suggests a long process of quiet alignment between physical possibility and biological function. There is also a comforting implication here. Quantum biology does not depend on rare or exotic conditions. It does not require life to operate on the edge of physical impossibility. It simply asks whether, among the many behaviours matter can exhibit, some are slightly more useful than others in the context of living systems. And if they are, evolution has had more than enough time to find them. This brings us to a subtle but important point. When we think about advantage, we often imagine improvement in a single direction: faster, stronger, larger. But biological advantage is often about balance. A system that is too rigid may fail when conditions change. A system that is too flexible may lack reliability. Quantum effects, when they appear in biology, may help strike this balance. They offer flexibility without chaos, exploration without loss of control. Not in a dramatic sense, but in the quiet way probabilities shift when more pathways are momentarily available. As we begin to see this, quantum biology stops feeling like a speculative curiosity and starts to resemble something more grounded, a natural extension of evolutionary logic into the deepest layers of physical behaviour. With this evolutionary lens in place, we are now prepared to consider a different question, one that once seemed like a decisive objection. If quantum effects are so fragile, so easily disturbed, how could they possibly survive inside the noisy environment of life at all? When people first encounter quantum ideas, there is often an instinctive reaction to ask whether they are too strange, too counterintuitive, or too fragile to belong in the living world. We worry about whether such effects are real enough, stable enough, or understandable enough to matter. Life does not share these concerns. Living systems do not pause to reflect on whether a mechanism feels elegant or disturbing. They do not ask whether an explanation satisfies human intuition. They're guided by a far simpler criterion. Does it work? If a process leads to survival more often than it fails, it is likely to persist. If it improves efficiency, even slightly, it is likely to remain. If it helps an organism reproduce or adapt in a changing environment, it becomes part of life's ongoing experiment. Everything else is eventually discarded. From this point of view, quantum mechanics is not special, it is simply part of the available toolkit. This pragmatic attitude is easy to miss because we tend to approach science as explanation seekers. We want clear causes, stable mechanisms, and rules that can be written down neatly. Biology, however, is less interested in explanations than in outcomes. It operates more like a long process of trial and retention than a carefully designed system. Imagine a craftsman who does not fully understand the physics of their tools, but knows which ones get the job done. Over time, the tools that work are used more often. The ones that do not are set aside. There is no need for a complete theory, only reliable results. Evolution works in much the same way. If a quantum effect occasionally improves the outcome of a biological process, that improvement does not need to be recognized or understood. It only needs to be repeated often enough to matter. Over time, structures that support or tolerate that effect become more common. Structures that interfere with it become less so. This is an important shift in perspective. We often imagine that for quantum effects to matter in biology, they must be carefully protected or deliberately maintained. But life does not aim for precision, it aims for usefulness. It does not need perfect control, it only needs consistent benefit. This is why quantum biology does not resemble quantum engineering. Engineered quantum systems are designed to preserve delicate states for as long as possible. They rely on isolation, extreme conditions, and constant correction. Living systems do none of this. They are open, noisy, and constantly interacting with their surroundings. And yet this openness may be exactly what allows certain quantum effects to be useful. Instead of trying to hold a fragile state in place, biology allows it to appear briefly, influence a process, and then fade away. The effect does not need to be preserved, it only needs to act. A momentary overlap of possibilities, a fleeting alignment, a brief enhancement of probability. These are enough. From an evolutionary standpoint, this makes perfect sense. Long-lived quantum states would be unnecessary and costly. Short-lived effects, embedded naturally in molecular processes, are far more compatible with the rhythms of life. This also helps explain why quantum biology does not require radical new forms of life or exotic biochemistry. The effects in question are subtle. They operate within familiar biological structures. They do not replace classical processes, they supplement them. Classical physics still does most of the work. Quantum effects offer small advantages at critical moments. Think of it like a well-practiced routine. Most of the time, it proceeds the same way it always has, but occasionally a small adjustment, almost imperceptible, makes the outcome slightly better. Over time, those adjustments become part of the routine, not because they were planned, but because they worked. This viewpoint also softens one of the most common objections to quantum biology, that it sounds too strange to be real. Strangeness is not a barrier in nature. Ineffectiveness is. Many features of life once seemed implausible or unnecessary. The idea that organisms could sense magnetic fields, or that tiny molecular machines could assemble themselves reliably, would have sounded far-fetched in earlier centuries. They are now well-established facts, not because they fit our expectations, but because they exist. Quantum biology asks us to apply the same humility. Instead of asking whether quantum effects belong in biology, we ask whether there is evidence that they help. Where they do, they are likely to persist. Where they do not, they quietly disappear. There is a certain calm in this way of thinking. It removes the need for grand claims or dramatic conclusions. It allows us to treat quantum biology as an extension of ordinary biological reasoning rather than a revolutionary break. It also reminds us that life does not optimize for understanding, it optimizes for continuity. From this perspective, quantum mechanics is not something life must overcome or tame. It is simply part of the landscape in which life emerged, a landscape filled with probabilities, fluctuations, and possibilities. Life learned to navigate that landscape long before we tried to map it. As we continue, this pragmatic lens will remain with us. It will help us see why some quantum effects matter, while others do not. Why biology uses them sparingly rather than extravagantly. And why the most interesting quantum influences are often the least dramatic. With that grounding in place, we can now turn toward a quieter and more speculative question, one that looks back toward life's earliest moments. Could some of these quantum-friendly tendencies be echoes of the environment in which life first began? When conversations about quantum biology reach this point, they often drift toward a question that feels both tempting and dangerous. It is tempting because it opens a wide imaginative landscape. It is dangerous because it can easily wander beyond what evidence supports. So tonight, we will walk carefully. The question is this: when life first emerged, did it do so in an environment where quantum effects were not just present but unavoidable? To begin, we need to picture the earliest Earth, not as a planet rich with forests, oceans teeming with life, and a breathable sky, but as a restless, unfinished world. The surface was warmer, energy sources were abundant and unevenly distributed. Molecules formed, broke apart, and reformed again in countless combinations. Nothing was stable for long. In this environment, the distinction between physics and chemistry was not yet sharp. Everything that existed was shaped by molecular interactions, and molecular interactions are governed at their deepest level by quantum rules. This does not mean that early life was doing quantum biology in any deliberate sense. It means something quieter. It means that the earlier steps toward life occurred in a world where quantum behavior was already woven into every interaction. Electrons shifted positions, bonds formed and dissolved, energy moved through molecular structures in ways that did not always follow a single, well-defined path. Probabilities mattered. Timing mattered. Chance mattered. In such a setting, it is reasonable to wonder whether some quantum behaviors became embedded, almost accidentally, in the earliest biological processes, not because they were chosen, but because they were already there. This idea is often described cautiously, using phrases like quantum residues or quantum echoes. These are not technical terms, but metaphors. They point to the possibility that some modern biological functions may still carry traces of how life first learned to operate in a quantum-governed molecular environment. It is important to be clear about what this idea does and does not claim. It does not claim that life originated because of exotic quantum effects alone. It does not claim that quantum mechanics somehow explains the origin of life by itself. The origin of life remains one of science's deepest open questions, involving chemistry, geology, energy flow, and time. What this idea suggests instead is much more modest. If early life emerged in conditions where quantum behavior naturally influenced molecular interactions, then some biological processes may have grown accustomed to those influences. Over time, as life became more complex. Those processes may have been preserved, not because they were quantum, but because they worked. In this sense, quantum biology does not need a dramatic beginning. It does not require a moment when life suddenly discovered quantum mechanics. It may simply reflect continuity. Life did not step into a classical world and later stumble upon quantum tricks. It arose in a world where quantum behavior was already the default at small scales. Classical behavior emerges only when large numbers of particles smooth out the underlying uncertainty. This framing also helps keep speculation grounded. We're not saying that modern organisms rely on the same quantum conditions that existed billions of years ago. Earth has changed, environments have shifted, life has adapted again and again. Any quantum influences that remain today must function within present-day conditions, and this is where evolutionary filtering returns to the story. If a quantum-sensitive process survived from early life into later forms, it would not be because it preserved some ancient state unchanged. It would be because, at every stage, it continued to offer a benefit. Evolution does not protect relics for sentimental reasons. It preserves functions that remain useful. So when we encounter quantum effects in modern biology, the most reasonable assumption is not that they are leftovers from a distant past, but that they are ongoing contributors, still relevant, still functional, still selected for. The idea of a quantum-influenced origin of life also invites a deeper reflection. We often imagine that life must conform to the environment in which it exists, but life also shapes itself around the rules of that environment. If uncertainty, probability, and fluctuation were fundamental features of the molecular world from the beginning, then it makes sense that life would incorporate them into its strategies. In this view, quantum mechanics is not an add-on to biology. It is part of the backdrop against which biology learned to exist. This perspective does something important. It removes the need for sharp boundaries. Instead of asking whether quantum biology is real or imaginary, we can ask how deeply quantum behavior is woven into different biological processes. Some may depend on it strongly, others only weakly, many not at all. That is not a weakness of the idea. It's exactly what we would expect from an evolutionary process that explores many possibilities and keeps only what continues to work. There is also a gentle philosophical lesson here. The more we learn about life, the more it seems to resist simple categories. It is neither purely mechanical nor purely mysterious. It does not fit neatly into the boxes we create for convenience. It occupies a middle ground, shaped by rules that are sometimes precise and sometimes probabilistic. Quantum biology, at its best, does not try to resolve this tension. It invites us to sit with it. As we prepare to move forward, away from speculation and toward concrete challenges, it is helpful to carry this humility with us. Not every question needs an immediate answer. Not every possibility needs to be confirmed or denied. Some ideas exist simply to remind us that nature is older, subtler, and more patient than our theories. And with that quiet awareness, we are ready to face what once seemed like the strongest objection of all. If quantum effects are so delicate, how could they possibly survive inside the noisy, crowded, ever-changing environment of living systems? To understand why quantum biology once seemed so unlikely, we need to spend a little time with a single idea, one that sounds technical at first, but becomes surprisingly gentle when we approach it the right way. That idea is coherence. Rather than defining coherence formally, let's imagine a scene. Picture a quiet pond at dawn. The surface is still, almost mirror-like. Now imagine a single pebble dropping into the water, rings spread outward in smooth, even circles. Each ripple knows where the others are. They reinforce one another, overlap in predictable ways, and create a pattern that feels orderly and calm. This is what coherence looks like. It is not about stillness. it is about coordination, about many parts moving together in a way that preserves their relationships even as they change. Now imagine tossing handfuls of pebbles into the pond all at once. The surface becomes busy. Ripples collide, cancel, and distort one another. Patterns blur. Order gives way to complexity. The water is still obeying the same physical rules, but the clear structure is harder to see. This loss of coordinated pattern is what scientists call decoherence. But it is important to notice something here. The ripples do not disappear. The water does not stop moving. The information is not destroyed. It is simply spread out, mixed in with everything else. Quantum coherence works in a similar way. At very small scales, particles and energy can behave like waves. When those waves move in step, when their peaks and valleys line up, coherence exists. This allows systems to explore multiple possibilities at once, not by choosing each option in turn, but by letting several options coexist briefly. This coexistence is not something we ever experience directly in daily life. It happens at scales too small and too fast for our senses, but its consequences can still matter. In physics laboratories, maintaining coherence is notoriously difficult. The slightest disturbance, heat, vibration, stray interactions, can disrupt the delicate alignment. This is why many engineered quantum systems require extreme conditions, near absolute cold, isolation, and careful shielding. From this perspective, biology seems like the worst possible place for coherence to survive. Living systems are warm, they are wet, they are crowded with activity. Molecules jostle constantly. Energy flows in uneven bursts. Everything interacts with everything else. If coherence requires calm, biology appears to offer none. And yet, this assumption rests on a subtle misunderstanding. Coherence does not need to last forever. It does not need to be perfect. It does not need to dominate a system. It only needs to persist long enough to influence what happens next. Return to the image of the pond. If the surface remains calm for even a brief moment, the ripples from a single pebble can travel far enough to shape the pattern that follows. Even if the water becomes turbulent afterward, that initial structure has already played its role. Biology operates on timescales where even unimaginably short moments can matter. Events that last for only a tiny fraction of a second can still guide chemical reactions, influence energy flow, or affect how signals propagate through a system. From this viewpoint, coherence becomes less fragile than it first appears. It is not something that must be preserved against all disturbance. It is something that must appear at the right time, in the right place, for just long enough. This reframing is one of the quiet revolutions in how scientists think about quantum biology. Instead of asking whether life can protect coherence indefinitely, the question becomes whether life can tolerate brief windows of coordinated quantum behavior. Windows that open and close naturally as molecules move, interact and rearrange themselves, and there is growing evidence that, in some contexts, it can. Another helpful way to think about coherence is through sound. Imagine a group of people humming the same note. If they are roughly in tune, the sound grows fuller and more stable. If they drift apart, the harmony dissolves into noise. But even a short moment of harmony can be enough to set a tone, to guide what follows. Quantum coherence works in much the same way. It allows multiple possibilities to reinforce one another briefly, shaping the direction a system takes before ordinary interactions return. Importantly, coherence does not imply control. There is no conductor, no plan, no awareness. It is an emergent property, a pattern that arises naturally under certain conditions and fades when those conditions change. This is why coherence fits surprisingly well with biological thinking. Biology is full of emergent patterns. From the folding of proteins to the firing of neurons, order arises not because it is imposed, but because the underlying components interact in just the right way. Coherence, in this sense, is not an alien concept in biology. It is a familiar one, seen at many scales, expressed here in a particularly subtle form. Understanding coherence in this gentle, intuitive way prepares us for the next step in the story. If coherence can exist briefly in biological systems, what happens when the environment inevitably disrupts it? Does everything fall apart? Or could disturbance itself play a more interesting role than we expect? As we continue, we will see that what looks like an enemy from one perspective may, from another, turn out to be an unexpected ally. If coherence is the moment when many possibilities briefly move together, then decoherence is what happens when the rest of the world joins in. Decoherence sounds like a harsh word. It carries the sense of something breaking down, of order collapsing into confusion. And in many discussions of quantum mechanics, it is presented almost as a villain, the force that destroys delicate quantum behavior and drags the universe back into the familiar classical world we recognize. But this picture is incomplete. To see why, it helps to return to something ordinary. Imagine sitting in a quiet room late at night. The air is still, sounds are soft and distant. In that moment, even the faintest noise, a ticking clock, a passing car, a rustle of fabric, stands out clearly. Patterns are easy to notice because there is little to interfere with them. Now imagine the same room during the day. Conversations overlap, footsteps pass by, phones buzz, doors open and close. The same sounds still exist, but they're no longer isolated. They blend into a background hum. Nothing has vanished. Everything is still there. It is simply mixed together. This is the essence of decoherence. In quantum systems, decoherence occurs when a delicate pattern of coordinated behavior becomes entangled with its environment. The system does not stop obeying quantum rules. Instead, its quantum features become distributed across so many interactions that they're no longer visible as a clean, isolated pattern. The information is not destroyed, it is dispersed. This distinction matters deeply for quantum biology. If decoherence were truly destructive, if it erased quantum effects completely, then biological systems would indeed be inhospitable places for them. Life is full of interactions. Everything touches everything else. There is no quiet room inside a cell. But if decoherence is better understood as blending rather than erasing, the picture changes. Biology does not need to preserve coherence indefinitely. It only needs coherence to appear briefly, influence a process, and then fade into the background. Once that influence has occurred, decoherence can take over without undoing the result. Think of it like a moment of alignment. Imagine adjusting the angle of a sailboat's sail just long enough to catch a favourable wind. The wind does not stay constant. The boat does not remain perfectly aligned, but that brief adjustment changes the course. Afterward, the environment can be as chaotic as it likes. The direction has already shifted. In biological systems, many important processes happen this way. They are guided, nudged, or biased by fleeting conditions. They do not require those conditions to persist. This is one reason scientists began to rethink the role of decoherence in living systems. Rather than asking how biology could eliminate noise, they began to ask whether biology could make use of it, whether disturbance might sometimes assist rather than hinder the flow of energy or information. This idea feels counterintuitive at first, especially if we're used to thinking of noise as something that degrades signals. In everyday life, static makes communication harder. Interference reduces clarity. We associate order with quiet and effectiveness with control. But nature often works differently. In some systems, a small amount of disturbance can actually improve performance. It can prevent a process from becoming stuck. It can help explore alternative pathways. It can shake a system just enough to move it out of an inefficient pattern. This insight is one of the most surprising developments in the study of quantum effects in biology. Noise, in the right amount and at the right time, can be helpful, not because it preserves coherence, but because it complements it. Coherence allows a system to explore possibilities together. Decoherence, and the interactions that cause it, can then guide the system toward a useful outcome by breaking ties, resolving ambiguity, or nudging energy along a more favourable route. In this sense, coherence and decoherence are not enemies. They are partners. Biology does not choose between perfect order and total chaos. It operates in the space between, a space where patterns form, dissolve, and reform continuously, where fleeting alignments shape outcomes without freezing them in place. This perspective also explains why attempts to copy biological quantum effects in the laboratory can be so challenging. Engineered systems often try to eliminate noise entirely. They aim for isolation, stability, and control. Biological systems do the opposite. They embrace interaction. They allow constant exchange with the environment. They are open by design. What looks like a weakness from an engineering standpoint can be a strength from a biological one. Living systems are not trying to hold on to delicate states. They're trying to move forward. They accept that everything will eventually be disturbed, and they design, through evolution, processes that take advantage of brief moments before disturbance takes over. Seen this way, decoherence stops being a fatal problem and becomes part of the rhythm of life. Patterns appear. They influence what happens next. They dissolve. New patterns take their place. Nothing needs to remain pure. Nothing needs to be protected forever. As we continue, this idea will become especially important when we look at specific biological examples. Places where energy, information, or direction seem to flow with surprising efficiency, not because the system is quiet, but because it is skillfully navigating its own noise. For now, it is enough to let go of the idea that quantum behaviour must be preserved in pristine isolation to matter. In the living world, usefulness does not come from perfection. It comes from timing, and with that thought gently settled, we can begin to approach one of the most unexpected discoveries in this field, a place where quantum coherence, disturbance, and biology appear to work together in a way that seems almost too elegant to be accidental. For a long time, the idea that quantum effects might matter in biology was met with polite skepticism, or, more often, quiet dismissal. Not because scientists lacked imagination, but because the basic assumptions seemed too strong to ignore. From the perspective of physics, living systems appeared fundamentally unsuitable for quantum behaviour. They are warm, they are wet, they are crowded, they are in constant motion. Every one of these features seemed hostile to the delicate coordination required for quantum effects to survive. In laboratories, maintaining quantum behaviour is famously difficult. Even in carefully controlled environments, coherence can vanish in an instant. That is why physicists go to such lengths to isolate their systems, cooling them to extreme temperatures, shielding them from vibrations, and minimizing every possible interaction with the outside world. Biology does none of this. A living cell is not isolated. It is open by necessity. Energy flows in and out. Molecules enter and leave. Signals arrive, are processed, and move on. There is no pause button, no moment of perfect stillness. From a traditional physics standpoint, this should spell disaster for any fragile quantum effect. And for decades, that assumption seemed reasonable. Quantum mechanics, it was thought, did its work quietly at the smaller scales. It explained why atoms bond and molecules form. Once those structures were in place, classical rules took over. Biology, in this view, was safely classical. Too large, too noisy, too warm for anything else. This belief became so ingrained that it was rarely questioned. But science has a habit of changing when observations refuse to cooperate. The first hints that something was amiss did not arrive as grand declarations. They came as small anomalies, measurements that did not fit expectations, efficiencies that seemed too high, behaviours that resisted classical explanation. At first, these were treated as puzzles to be solved within existing frameworks. New models were proposed, additional mechanisms were suggested. But over time, a pattern began to emerge. Some biological processes appeared to be operating with a level of effectiveness that classical reasoning struggled to account for. This did not immediately lead to claims about quantum biology. Scientists are cautious by nature. Extraordinary claims require extraordinary evidence, and caution was warranted. But the door had been opened. The real shock came not from a single experiment, but from the accumulation of results pointing in the same direction. Evidence that suggested quantum effects might persist, briefly and usefully, inside living systems after all. What made this so unsettling was not just the implication, but the contrast. Engineers struggle to keep quantum systems stable even under ideal conditions. Yet biology, with none of those protections, appeared to manage just enough coherence to matter. Not for long, not perfectly, but long enough. This reversal of expectations forced a re-evaluation. Perhaps the problem was not that biology was too messy for quantum effects. Perhaps the problem was that our definition of what quantum effects should look like was too narrow. We had been searching for pristine, long-lived quantum states, because that is what engineering requires. Biology, it turned out, was playing a different game. Living systems were not preserving coherence against all odds. They were allowing it to arise naturally, briefly, within the flow of ordinary molecular activity. They were not fighting the environment. They were using it. This realization marked a quiet turning point. Quantum biology was no longer dismissed as impossible. It became something to investigate carefully, case by case, with attention to detail and restraint. The question shifted from, can this happen at all, to, under what conditions does it happen and does it matter? Importantly, this shift did not require abandoning skepticism. It required refining it. Not every claim about quantum effects in biology holds up under scrutiny. Many proposed mechanisms remain speculative. Some ideas, once examined closely, do not survive further testing. This is exactly how science should work. What changed was the recognition that the door was not closed. Biology had surprised physics before. It had revealed forms of organization, regulation, and efficiency that no one had predicted in advance. Molecular machines, self-assembling structures, networks that process information without centralized control, each of these once seemed implausible. Quantum biology began to join that list, not as a revolutionary overthrow of existing knowledge, but as an extension of it. The shock, in retrospect, was not that quantum effects might appear in biology. It was that we had assumed, without sufficient evidence, that they could not. This moment of humility is worth lingering on. Science progresses not only through discovery, but through the quiet correction of assumptions, through the recognition that a reasonable idea, held too tightly, can become a barrier rather than a guide. Quantum biology reminds us of this. It encourages a different kind of attention, a willingness to look closely at small effects, to take seriously phenomena that operate at the edge of detectability, to accept that usefulness does not require grandeur. In the living world, success often comes from subtlety. As we move forward from this turning point, the discussion becomes more concrete, less about whether quantum biology is possible, and more about where it appears most convincingly. One of the clearest examples lies in a process so familiar that we often take it for granted. A process that quietly powers almost all life on Earth, the way plants capture light. Nearly everything alive on Earth depends, directly or indirectly, on a process so familiar that it often fades into the background of our attention. Photosynthesis. It happens quietly, constantly, across forests, fields, oceans and gardens. Leaves turn toward the light. Algae drift near the surface of water. Tiny organisms, invisible to the naked eye, absorb sunlight and begin a transformation that feeds almost all life that follows. Plants use light to build sugars. Animals eat plants or eat other animals that ate plants. Oxygen fills the air as a byproduct. Energy captured from the sun moves through food chains, ecosystems, and generations. It is difficult to overstate how central this process is. Without it, Earth would be a very different place. Quiet, barren, and largely lifeless. Because photosynthesis is so fundamental, it is often taught early and taught simply. Light arrives, energy is absorbed, chemical reactions follow. The story feels complete, and for a long time, that story seemed sufficient. But as scientists looked more closely, they began to notice something subtle and unsettling. Photosynthesis works not just well, but remarkably well, with an efficiency that seems almost too good for such a noisy, uncontrolled environment. This efficiency is not about speed alone, it is about reliability, about how consistently energy moves from the moment light is absorbed to the places where it can be used, without getting lost along the way. To appreciate why this is surprising, imagine energy as a traveller. Light arrives at a leaf and is absorbed by special molecules. From there, the energy must make its way through a complex landscape of molecular structures to reach a destination where it can be stored and used. Along this journey, there are many possible paths. Some are direct, others are winding. Some lead to dead ends where energy can be wasted as heat. In a purely classical picture, this journey would look like trial and error. Energy would move step by step, sampling one route, then another, occasionally backtracking, occasionally getting stuck. Given enough time, it would usually find its way, but not always, and not with extraordinary consistency. Yet real photosynthetic systems perform this task with astonishing reliability. This raises a gentle question. How does energy know where to go? This is not meant literally. Energy does not make decisions. But the question points towards something deeper. It suggests that the movement of energy through a photosynthetic system may be guided by principles that are not fully captured by simple step-by-step models. To explore this idea, it helps to shift how we imagine the journey. Instead of thinking of energy as a traveller choosing paths one at a time, imagine it as something more fluid, less like a person walking through a maze and more like water released onto a landscape. Water does not choose a single path and commit to it. It spreads, it explores, it flows downhill guided by the shape of the terrain. In doing so, it naturally finds routes that require the least effort, often without ever deciding in the way we might expect. This image turns out to be surprisingly useful. Inside photosynthetic systems, energy moves through networks of molecules arranged in specific patterns. These patterns create an energy landscape, with gentle slopes and subtle variations. When light is absorbed, energy does not need to test each path in turn. It can, briefly and quietly, explore several possibilities at once, not in a conscious way, not in a controlled way, but in a manner that reflects the underlying physical rules governing the smaller scales of matter. This is where quantum ideas begin to enter the story, not as exotic additions, but as natural descriptions of how energy behaves when confined to very small spaces. At these scales, energy does not always move like a solid object hopping from place to place. It behaves more like a spreading influence, sensitive to multiple routes simultaneously. For a fleeting moment, it can respond to the overall shape of the system rather than a single narrow path. Importantly, this does not mean photosynthesis is doing something magical. It does not violate classical physics. Instead, it operates in a regime where classical and quantum descriptions overlap, and where certain quantum-like behaviours can quietly enhance performance. The result is not perfection, but something close enough to be remarkable. Photosynthetic systems guide energy efficiently, not by eliminating uncertainty, but by allowing energy to explore possibilities before settling into a useful outcome. The journey is shaped by structure, timing, and interaction, not by rigid control. What makes this especially striking is the environment in which it happens. Photosynthesis takes place in warm, wet, vibrating systems. Molecules move, temperatures fluctuate, interactions are constant. This is not a calm laboratory. It is a living, breathing environment, and yet within this environment energy moves with grace. This suggests that the efficiency of photosynthesis is not an accident, nor is it a fragile miracle. It is the result of a long evolutionary process that shaped molecular structures to work well under real-world conditions. Conditions filled with noise, motion, and change. Seen this way, photosynthesis becomes more than a chemical reaction. It becomes an example of how life navigates complexity. Instead of forcing order onto a chaotic system, it uses structure to guide flow. Instead of demanding certainty, it allows exploration. Instead of resisting disturbance, it operates within it. As we sit with this idea, there is no need to rush toward detailed mechanisms or technical explanations. Those belong to another kind of discussion. What matters here is the shift in perspective. Photosynthesis works not by simplifying the world, but by embracing its richness. This realization prepares us for the next step in the story. If energy can explore possibilities and move efficiently through a noisy environment, what role does that noise itself play? Could disturbance, rather than being a problem to overcome, be part of the solution? That question will guide us gently onward, deeper into this quiet success story written in light and leaves. As we continue to linger with photosynthesis, it becomes helpful to slow the picture down even further, not to add complexity, but to notice something subtle about how energy behaves once it enters a living system. When a particle of light is absorbed by a photosynthetic molecule, the energy does not arrive with instructions. It is not told where to go, which path to take, or how quickly to move. It simply appears within a crowded molecular environment, surrounded by many possible routes forward. In the way we usually imagine motion, this energy would begin a kind of search. It would move step by step, testing one path then another. If it reached a dead end, it would turn back. If it found a better route, it would continue. This is how we tend to picture problem solving: sequential, deliberate, and guided by choice. But at very small scales, energy does not need to behave this way. Instead of choosing a single route and committing to it, energy can briefly behave as if it is sampling many routes at once, not by racing along each one individually, but by spreading out, responding to the overall structure of the system in a more holistic way. A helpful image here is water released onto a hillside. Water does not stand at the top considering which channel to follow. It does not try one path, then abandon it for another. It spreads, it flows, it responds to slopes, grooves, and textures all at once. In doing so, it naturally finds efficient routes downward, often without ever forming a single narrow stream. In photosynthesis, energy behaves in a similar spirit. The molecular structures that guide energy through a photosynthetic system create a landscape, one shaped by distances, orientations, and interactions. When energy enters this landscape, it does not need to evaluate each option separately. For a fleeting moment, it can be sensitive to the entire layout. This sensitivity allows energy to move in ways that feel almost intuitive. It tends toward pathways that lead efficiently to its destination, not because it is directed, but because the system itself gently guides it. This does not require us to imagine anything mystical. It is simply a consequence of how energy behaves when it is confined, structured, and allowed to interact with its surroundings. One of the most remarkable outcomes of this behavior is efficiency. Photosynthetic systems are extraordinarily good at transferring energy from the point of absorption to the point of use. Very little is wasted, very little is lost along the way. For a process operating in such a noisy environment, this level of performance is striking. What makes it even more striking is that this efficiency does not come from rigid control. There is no single, fixed path that energy must follow. Instead, there is flexibility. Multiple routes remain available. The system does not collapse if one pathway is blocked or disturbed. Energy simply flows around the obstruction, guided by the broader landscape. This flexibility is a hallmark of living systems. It is what allows them to remain functional in the face of change, and it is also what makes them compatible with quantum-inspired behaviors. At this point, it is important to address a common misunderstanding. When people hear that energy can explore multiple possibilities, they sometimes imagine complex calculations or exotic states that need to be carefully protected. But nothing like that is required here. The behavior we're describing does not depend on long-lasting delicacy. It depends on timing. The moment of exploration is brief, almost unimaginably brief. But it happens at exactly the right time, when energy first enters the system and before it becomes locked into a specific outcome. Once the energy is settled into a useful pathway, ordinary interactions take over. Classical behavior resumes. The quantum-like exploration has already done its work. This is why the term exploration is so useful. It captures the idea of openness without intention. Energy is not solving a problem. It is responding to possibilities. It is moving in a way that reflects the structure it inhabits. And because this structure has been shaped by evolution, the possibilities it offers tend to be useful ones. Over millions of years, photosynthetic systems have been refined to guide energy efficiently under real-world conditions. The molecular arrangements that support this gentle exploration are not accidental. They are the result of countless small adjustments that favoured reliable performance. In this light, the efficiency of photosynthesis becomes less mysterious. It is not the product of perfect design, nor is it a lucky coincidence. It is the outcome of a long conversation between physical possibility and biological necessity. There is also something quietly beautiful about this picture. Energy does not rush. It does not hesitate. It simply spreads into the space available to it, guided by the contours of the system. It finds its way not through force, but through fit. This way of thinking invites us to reconsider how we interpret efficiency more broadly. We often associate efficiency with control, precision, and rigidity. Photosynthesis suggests a different model, one based on openness, responsiveness, and balance. And this model works. As we rest with this idea, we can begin to sense why photosynthesis became one of the first and strongest examples in the study of quantum biology. It shows how quantum-like behavior can appear not as an exception, but as a natural extension of how living systems already function. It also sets the stage for an even more surprising insight. If energy exploration can enhance efficiency, what happens when the system is gently disturbed? When the environment adds a bit of randomness, a bit of motion, a bit of noise? Counterintuitively, the answer may be that things work even better. Up to this point, it might seem that the success of photosynthesis depends on a delicate balance. Energy exploring possibilities briefly, guided by structure, before settling into a useful path. But there is another layer to this story, one that challenges an assumption many of us carry without noticing. We tend to think of noise as a problem. In everyday life, noise disrupts conversations. It blurs signals. It makes it harder to focus. When something is important, we try to protect it from interference. We close doors, lower our voices, and search for quiet. So it feels natural to assume that, in photosynthesis, noise would be an enemy. That vibrations, random motions, and environmental fluctuations would interfere with the smooth movement of energy. But nature often surprises us. As researchers studied photosynthetic systems more closely, they began to notice something unexpected. In certain situations, a small amount of disturbance did not reduce efficiency, it improved it. This idea can feel unsettling at first, because it seems to contradict everything we've just discussed. If energy benefits from exploring possibilities together, shouldn't noise disrupt that exploration? The answer turns out to be more subtle. To see why, imagine walking through a gently sloping landscape in the dark. You can feel the ground beneath your feet. You can sense which direction leads downhill, but occasionally you might pause, unsure whether you've reached a flat patch or a shallow dip. You hesitate, unsure how to proceed. Now imagine that a light breeze begins to blow, brushing against you just enough to remind you of the broader terrain. That small disturbance does not push you off course. It helps you regain direction. In photosynthesis, something similar can happen. As energy explores the landscape of possible pathways, it can occasionally linger in places that are not ideal. These are not traps in a dramatic sense, but regions where progress slows. If nothing disturbs the system, energy might remain there longer than necessary. A small amount of environmental motion, tiny vibrations, gentle fluctuations, can provide just enough of a nudge to move energy along, not randomly and not destructively, but constructively. This is the heart of the idea often described as noise-assisted transport. Rather than thinking of noise as chaos, it is more helpful to think of it as texture. It adds richness to the landscape. It prevents the system from becoming too smooth, too predictable, too easily stuck. Importantly, this does not mean that more noise is always better. Too much disturbance would indeed overwhelm the system, scattering energy before it can be used. What matters is balance. Biology excels at operating in this balanced zone. Living systems are not silent. They're alive with motion. Molecules vibrate, structures flex, temperatures fluctuate. These movements are not incidental. They are part of the environment in which biological processes evolved. Over time, photosynthetic systems appear to have adapted to this reality. Their structures are not designed to eliminate noise, but to work with it, to allow just enough disturbance to keep energy moving without letting it drift away. This perspective transforms how we think about efficiency. Efficiency, in this context, is not about perfect order. It is about dynamic cooperation. A system that is too rigid may trap energy. A system that is too chaotic may lose it. The most effective systems live in between, where gentle disturbance supports flow. There's a quiet lesson here that extends beyond photosynthesis. In many areas of science and life, we equate improvement with reduction. Less noise, less variability, less uncertainty. But biological systems often improve by integration rather than elimination. They incorporate variability into their functioning, turning what looks like a weakness into a strength. This is not accidental. It reflects the conditions under which life evolved. Photosynthesis did not develop in a controlled laboratory. It developed under sunlight that fluctuated with clouds and seasons, in environments shaped by wind, water, and temperature changes. The systems that survived were those that could perform reliably under these conditions, not those that required perfect stability. Seen this way, noise-assisted transport stops feeling like a clever trick and starts to feel inevitable. If energy must move through a complex landscape, and if that landscape is constantly in motion, then mechanisms that can use motion to their advantage will naturally outperform those that cannot. This idea also reinforces something we have touched on before. Quantum-like behaviours in biology do not operate in isolation. They are not preserved in pristine form. They are embedded in a living context, interacting continuously with classical processes. Coherence and disturbance appear together, shaping outcomes collaboratively. In photosynthesis, exploration allows energy to sense possibilities. Noise helps resolve them. Together they guide energy toward useful destinations with remarkable consistency. There is a philosophical resonance here that is hard to miss. Nature does not thrive by eliminating imperfection. It thrives by learning how to work within it. The same disturbances that threaten order can also create opportunity, depending on how they are integrated. As we allow this idea to settle, it invites a broader reflection. Perhaps the success of photosynthesis is not just a story about energy and molecules. Perhaps it is also a story about adaptability, about finding ways forward in an ever-changing world. With that reflection gently in mind, we can now prepare to turn our attention elsewhere. Photosynthesis shows us how energy moves efficiently through a noisy environment. But there are other biological mysteries that invite a similar kind of thinking. Mysteries not about energy flow, but about direction. How does a bird flying through the night know which way to go? Imagine standing beneath a night sky, far from city lights. The air is cool, the stars are steady. Somewhere above you, unseen and unheard, a bird is flying. It is not following roads, it is not tracing coastlines or mountain ranges, it is not guided by streetlights or familiar landmarks. In many cases, it is travelling thousands of kilometres across open ocean, desert or darkness, guided by something far more subtle, and it arrives. Year after year, generation after generation, birds migrate with a precision that feels almost implausible. They leave one continent and return to another. They cross hemispheres. They navigate storms, shifting winds and unfamiliar terrain. Many do this at night, when visual cues are limited or absent. This ability has fascinated humans for centuries. Early explanations were simple and often poetic. Birds, it was said, followed the stars, or they remembered the shape of the land, or they sensed changes in temperature or smell. Each of these ideas captured part of the truth, but none fully explained the phenomenon. As science advanced, the mystery deepened rather than disappeared. Experiments showed that birds could navigate even when familiar landmarks were removed. They could orient themselves on cloudy nights. They could adjust their routes when displaced far from expected paths. Something else was guiding them, something global, invisible, and always present, the Earth itself. Specifically, Earth's magnetic field. This discovery raised new questions. The planet's magnetic field is weak. It does not push or pull in ways we can feel. It does not point clearly like a signpost in the sky. Yet birds seemed able to sense it with remarkable reliability. How? To appreciate why this is puzzling, Consider your own experience. You move through the world using cues that are tangible and local. You see landmarks. You feel slopes underfoot. You hear sounds grow louder or softer as you approach or retreat. Direction for us is something we infer from immediate surroundings. A magnetic field offers none of this. It does not announce itself. It does not have edges or boundaries. It does not look different from one place to another in any obvious way. It simply exists, quietly threading through space, wrapping the planet in an invisible structure. For a long time, it was unclear how any biological system could sense such a thing directly. Traditional explanations struggled. Mechanical models did not fit the data. Chemical reactions alone seemed too insensitive. Neural processing by itself could not explain how the information was first detected. The mystery remained. What made this puzzle especially intriguing was its consistency. Birds did not just sometimes succeed, they succeeded reliably, under a wide range of conditions. Their sense of direction was robust, adaptable, and resilient. This suggested that whatever mechanism was at work, it was not fragile. It was not a delicate trick that failed easily. It was something that had been refined by evolution to work under real-world conditions. At this stage, it is important to pause. We are not trying to solve the mystery immediately. In fact, rushing toward an answer would undermine something essential. The power of this story lies in the experience of the question itself. Imagine being a bird, lifted into the air by instinct and muscle, guided not by maps or memory, but by a sense so subtle that it borders on the unimaginable. Imagine feeling direction without seeing it, orientation without landmarks, movement guided by something that never quite appears. This is not a problem to be solved on paper. It is a phenomenon to be felt. From this perspective, bird navigation becomes more than a technical question. It becomes a reminder of how differently other organisms experience the world. What is invisible to us may be richly informative to them. What feels abstract to us may be deeply embodied for them. As scientists continued to explore this mystery, they began to suspect that the answer might not lie in a single sense, but in an interaction. A process that didn't rely on force or pressure, but on sensitivity, on timing, on fleeting states that could respond to the faintest of cues. Slowly, carefully, a new idea entered the discussion, one that had once seemed out of place in biology: quantum effects, not as something exotic or mystical, but as a way to explain how extremely weak signals could influence biological processes at just the right moment. How information could be extracted not by brute strength, but by alignment. This idea did not arrive fully formed. It emerged through years of observation, debate, and cautious experimentation, and even today it remains an active area of research, refined continually as new evidence appears. What matters for our journey is not the final verdict, but the shift in perspective. Bird navigation invites us to consider that biology may sometimes rely on sensitivity rather than certainty, on processes that operate at the edge of detectability, yet remain reliable through timing and structure. As we prepare to explore one of the most intriguing proposals in this area, it is worth holding on to the feeling of wonder rather than reaching for resolution. The bird flies, the planet turns, direction is sensed without being seen, and somewhere in this quiet alignment between life and earth, a deeper story begins to unfold. To begin approaching how a bird might sense something as faint as Earth's magnetic field, it helps to let go of a familiar expectation. We often imagine a compass as a solid object, something that points, something that settles, something that holds still once it finds direction. But what if a compass did not point? What if it flickered? What if it appeared only briefly, formed from light itself, and vanished almost as soon as it emerged, leaving behind not a direction but a subtle bias, a quiet tilt, a sense of this way rather than an arrow? This is the spirit of the idea that has captured so much attention in the study of bird navigation. The proposal begins with light. When certain molecules in a bird's eye absorb light, they enter a brief, excited state. This state does not last long. It is not stable. It exists only for a moment before the system relaxes again, but during that moment something remarkable can occur. The absorbed light can create a pair of linked reactions, two parts of a process that are born together and briefly remain connected in their behaviour. Not connected in space like gears, and not connected by force like magnets, but connected in timing and influence. They respond together. This pairing is fleeting, it is delicate, it is easily influenced by the surrounding environment, and that is precisely why it is useful. Because during this brief window, the paired reactions are sensitive to extremely small influences, small enough to notice the presence of Earth's magnetic field, not by measuring its strength, but by responding to its orientation. To make sense of this, imagine a shimmer on the surface of water. The water itself is still. The shimmer does not push the water. It does not carve a channel. It simply tilts the way light reflects depending on the angle of the sun. A small change in orientation produces a subtle but noticeable difference in appearance. In a similar way, the paired reactions created by light in a bird's eye may be gently tilted by the planet's magnetic field. The field does not force anything to move. It does not overwhelm the system. It simply shifts probabilities. The outcome is not a signal that says north or south. It is more like a pattern of light and dark, a faint contrast that changes as the bird's head turns. Direction emerges not as a point, but as a relationship. This idea explains several puzzling observations at once. It explains why vision matters for navigation. Birds often struggle to orient themselves in complete darkness, even when other cues remain available. It explains why the sense appears to depend on light of specific colours rather than brightness alone. And it explains why the mechanism is sensitive to disruption. Certain artificial conditions can interfere with it, even when other senses remain intact. What makes this proposal especially compelling is not its strangeness, but its restraint. It does not require birds to maintain long-lasting, perfectly isolated quantum states. The paired reactions exist only briefly. They do not need protection from the environment. In fact, their sensitivity depends on interaction. The surrounding noise does not destroy the effect, it helps define it. Timing is everything. The paired state must last long enough to be influenced, but not so long that it becomes locked into a rigid outcome. It must be open to disturbance, but not overwhelmed by it. This balance mirrors what we've already seen in photosynthesis. Brief coherence guided by structure, working within a noisy world. Seen this way, the bird's compass is not a device, but a process. A recurring moment, triggered by light, shaped by the environment, and interpreted by the nervous system as a sense of orientation. The bird does not see magnetic fields in the way we see colours or shapes. It experiences a modulation, a change in visual perception that depends on direction. As the bird turns, the pattern shifts. As the planet curves beneath it, the relationship remains. This also helps explain why the experience is difficult to imagine. We're used to senses that report objects, things with edges, distances, and locations. This sense reports relationships. It tells the bird not where something is, but how it is lined within a larger field. There is something quietly profound about this. A living organism using light, sensitivity, and fleeting states, aligns itself with the structure of an entire planet, not through force, not through calculation, but through resonance. And yet, for all its elegance, this idea remains an area of active investigation. Researchers continue to test, refine, and challenge it. Alternative explanations are explored, details are debated. This is how science moves forward. What matters for our story is not certainty, but plausibility. The radical idea, gentle, fleeting, and grounded in known physical behaviour, offers a way to connect biology with quantum sensitivity without exaggeration. It respects the constraints of living systems. It honours the messiness of the real world. It also reinforces a theme that has been quietly unfolding throughout our journey. Life does not need to master the universe to navigate it. It only needs to be sensitive in the right way at the right time. As we prepare to move on, the image of the bird remains with us, not as a machine executing instructions, but as a living system tuned to patterns we rarely notice. Light enters the eye. A brief pairing forms, the planet's field whispers, direction emerges, and without ever seeing the path ahead, the bird continues on its way. When we think about movement, we almost always imagine a path, a line connecting where we are to where we want to go, a sequence of steps, a distance that must be crossed gradually and deliberately. Even when we think abstractly, our minds return to this image. Progress as travel through space, guided by landmarks and choices. But the story of bird navigation invites us to loosen this picture. What if finding direction does not always require tracing a path? What if, in some cases, direction can be sensed without measuring distance, without calculating routes, without even committing to a single trajectory in advance? To explore this idea, it helps to imagine something familiar. Picture yourself standing in a gentle rain, eyes closed. You cannot see where the clouds are or how far away they stretch, yet you can still sense the wind. You feel which way it brushes against your face, which side of your body cools first, which direction the air seems to favour. You're not tracking where the wind began or where it will end. You're simply aligned with it. Bird navigation, at its most subtle, may work in a similar way. Rather than calculating a route across thousands of kilometres, the bird continuously aligns itself with a global pattern. Direction is not a destination stored in memory, it is a relationship renewed moment by moment. This way of navigating does not require the bird to know where it is in the way we understand knowledge. It requires sensitivity, a readiness to respond to small changes, a capacity to remain aligned as conditions shift. From this perspective, the bird is not following a line across the earth. It is maintaining a conversation with the planet itself. This idea helps explain why the process does not feel mechanical. A mechanical system relies on fixed reference points. If those points change or disappear, the system fails. Bird navigation does not fail so easily. It adapts, it adjusts, it compensates for drift, wind, and displacement. That resilience makes sense if the system is not anchored to specific locations, but to orientation. Orientation does not depend on distance, it depends on alignment. An alignment can be sensed without moving. This is where quantum-inspired ideas quietly deepen the picture. In classical thinking, movement requires traversal. To get from one place to another, something must pass through the space in between. But at very small scales, this intuition begins to soften. Systems can respond to structure without tracing every intermediate step. They can be influenced by relationships rather than paths. In the case of bird navigation, the paired reactions we discussed earlier do not send signals across space. They do not travel from one end of the system to another. Instead, they respond locally to a global condition, the orientation of Earth's magnetic field. The bird does not detect a signal arriving from the north. It experiences a pattern that changes with direction. As the bird turns, the pattern shifts. Alignment is revealed through contrast, not distance. This is why the sense can feel so elusive. There's nothing to point to, nothing to isolate, nothing to extract and examine like a compass needle. The information exists only in relation to the bird's orientation, and only while the process is active. Once again, timing matters. The sense of direction is not stored permanently. It is refreshed continually. Each moment of light absorption offers a new opportunity to align. Each moment of alignment informs the next movement. Navigation becomes a flow, not a calculation. This challenges a deeply ingrained assumption that understanding requires representation. We often believe that to navigate, an organism must hold an internal map, that it must know where it is and where it is going in explicit terms, but birds may not need maps at all. They may need only a way to remain oriented within a field that already contains directional information. This does not make their navigation simpler, it makes it different. It replaces the idea of planning with the idea of attunement. There is something quietly profound about this shift. It suggests that intelligence does not always operate by modelling the world and acting upon those models. Sometimes it operates by staying sensitive to patterns and letting action emerge naturally. In this sense, bird navigation becomes a lesson not just in biology, but in perspective. We tend to think of motion as effortful, of travel as something that requires constant decision-making, but the bird's flight suggests another possibility: movement guided by alignment, sustained by sensitivity, and supported by the environment rather than imposed upon it. The quantum aspects of this story do not make it stranger, they make it gentler. They show how extremely subtle effects can matter, not by overpowering a system, but by biasing it slightly, again and again, until direction becomes stable through repetition. Nothing dramatic happens in any single moment. There is no leap across space. There is only a quiet correction, continuously applied. As we step back from this image, it becomes clear why this example resonates so strongly with the broader themes of quantum biology. Once again, we see that usefulness does not require control, that effectiveness does not demand precision in the way we usually imagine it, that life can solve problems not by conquering complexity, but by flowing within it. The bird does not defeat distance, it does not ignore space. It simply does not need to measure either one explicitly. It flies, aligned with patterns larger than itself. And as we allow this image to settle, we find ourselves arriving at a more reflective place. One where the boundaries between physics and biology, between mechanism and meaning, begin to soften. Some questions, we will soon discover, begin to lose their sharp edges when viewed this way. As we arrive at this point in our journey, something subtle begins to shift. For much of our exploration, we've been asking questions. How does energy move so efficiently? How can noise help rather than hinder? How does a bird sense direction without landmarks? Each question has guided us forward, opening new perspectives and inviting deeper understanding. But now, the questions themselves begin to change. In quantum mechanics, there is a quiet lesson that often feels unsettling at first. Some questions simply do not apply in the way we expect them to. They are not wrong exactly, but misplaced, like asking which note a chord really is, or where a wave truly ends. Consider a simple example. Imagine watching a shadow move across the ground as clouds drift overhead. You can describe the shadow shape, you can track its motion, but if you ask where the shadow itself exists as an object, the question begins to dissolve. The shadow is not a thing that travels independently. It is a relationship between light, surface, and obstruction. In quantum mechanics, many familiar questions behave like this. We're used to asking whether something is here or there, whether it is one thing or another, whether it followed this path or that one. These questions come naturally to mind shaped by everyday experience, but at very small scales and in very subtle processes, the world does not always cooperate. When energy explores multiple possibilities in photosynthesis, asking which path it really took may not have a meaningful answer. When a bird aligns with Earth's magnetic field through fleeting sensitivity, asking where the signal comes from may miss the point. The behaviour emerges from relationships, not from isolated objects. This does not mean reality is vague or unknowable. It means that our language, shaped by solid objects and clear boundaries, sometimes struggles to keep up. Quantum biology brings this tension into focus because it sits at the boundary between worlds we feel we understand. Biology feels tangible. We can see organisms, touch leaves, watch birds fly. Quantum mechanics feels abstract, distant, and mathematical. When these domains overlap, our intuition hesitates. We want to know exactly what is happening. We want to point to a mechanism and say, there it is. But some processes resist this kind of framing. They are not located in one place or one moment. They unfold through interaction, timing, and context. This is why questions like, was the energy really on this path or that one? Or, is the bird really sensing the magnetic field, can be misleading. They assume that reality must choose one clear option before anything meaningful can occur. Quantum mechanics suggests otherwise. It allows for situations where possibilities matter, even if none of them is selected in the way we expect. In photosynthesis, energy does not need to commit to a single route in advance. In bird navigation, sensitivity does not require a direct signal that can be isolated and measured like a force. In both cases, usefulness arises from openness rather than certainty. This realization invites a kind of intellectual relaxation. Instead of forcing answers into familiar categories, we can allow some questions to soften. We can accept that not every how can be reduced to a simple sequence of events, and not every where refers to a location in space. There is a quiet freedom in this. It doesn't weaken science, it strengthens it. By recognizing the limits of certain questions, scientists can ask better ones, questions that align more closely with how systems actually behave. For example, instead of asking whether a quantum effect is really present in a biological system, researchers ask whether including quantum descriptions improves predictions, whether it helps explain observed behavior, whether it leads to testable insights. This shift from metaphysical certainty to practical usefulness echoes something we encountered earlier. Evolution does not care how something works in principle, it cares whether it works in practice. Quantum biology, seen this way, is less about redefining reality and more about refining our descriptions. It asks us to use the tools that best fit the phenomena, even if those tools feel unfamiliar. There is also a personal dimension to this insight. We often carry a quiet expectation that understanding means closure, that once we understand something, the questions will stop. But in science, and perhaps in life, understanding often does the opposite. It opens new spaces for curiosity while dissolving old assumptions. Some questions fade not because they are answered, but because they are no longer needed. As we let these ideas settle, the pace naturally slows. There is no rush to resolve every uncertainty. The goal is not to reach a final conclusion, but to rest comfortably within a more flexible view of the world. Reality, it seems, does not always arrive neatly packaged. It flows, it overlaps, it reveals itself through relationships rather than declarations. and perhaps that is not something to resist. As we prepare for our final reflection, we can carry this gentler posture with us, a willingness to let go of sharp edges, to allow mystery to remain without discomfort, and to appreciate that understanding can coexist with openness. In that space, curiosity becomes quieter, and thought begins to drift toward rest. As we come to the end of this long, unhurried exploration, it is worth pausing, not to summarize facts, but to notice a feeling that may have been quietly growing along the way, a sense of humility. Throughout this journey, we have seen ideas that once felt improbable slowly become plausible. We have watched assumptions soften, not because they were careless, but because nature turned out to be more subtle than expected. Again and again, living systems revealed ways of working that did not fit neatly into the categories we had prepared for them. Photosynthesis did not wait for us to understand energy landscapes. Birds did not need our permission to sense the planet beneath them. Life, in all its forms, simply worked, long before it was named, measured, or modelled. This is perhaps the deepest lesson quantum biology has to offer. It reminds us that biology is not merely an application of physics. It is not a passive stage on which physical laws perform. It is an active participant, a teacher, in its own quiet way, revealing how physical principles can operate under conditions far messier and richer than any laboratory. For a long time, physics set the rules and biology was expected to follow. When something did not fit, biology was often treated as an exception or an approximation. Quantum biology reverses that posture slightly. It suggests that by studying life carefully, we may learn new ways of thinking about physics itself. Not new laws necessarily, but new regimes, new balances, new ways in which delicate effects can matter without dominating. Life shows us that usefulness does not require perfection, that sensitivity can coexist with noise, that fleeting moments can shape lasting outcomes. These are not the lessons of idealized systems, they are the lessons of systems that endure. There is something deeply comforting about this perspective. It tells us that nature does not rely on precision alone. It relies on fit, on responsiveness, on the ability to work within constraints rather than escaping them. Life did not wait for quiet conditions or simplified environments. It emerged, adapted, and flourished amid complexity. Quantum biology, at its heart, is not about making life seem stranger. It is about making our picture of life more honest. It invites us to see living systems as they are, not fragile miracles balanced on the edge of collapse, but resilient processes shaped by long histories of interaction with the dynamic world. Processes that can use subtle physical effects without being defined by them. This shift has implications beyond science. It challenges the way we think about understanding itself. We often imagine that knowledge progresses by reducing mystery, by replacing uncertainty with clarity. But here, clarity does not arrive by stripping away nuance. It arrives by embracing it. We do not fully understand photosynthesis because we have listed every step. We understand it better because we see how structure, motion, and timing work together. We do not appreciate bird navigation because we have isolated a single signal. We appreciate it because we recognize how sensitivity, environment, and perception intertwine. In this sense, quantum biology does not close doors. It opens them gently. It encourages us to be careful with our questions, to ask not only what happens, but how our expectations shape what we notice, to remember that some of the most important processes in nature operate quietly, without spectacle, without announcement. As we allow these thoughts to settle, it becomes easier to release the urge to resolve everything. We do not need a final answer about how deeply quantum effects reach into biology. We do not need to decide which phenomena count and which do not. Science will continue to explore these questions in its own time, with patience and care. For now, it is enough to recognize that life is not indifferent to the rules of the universe, but neither is it constrained by our first intuitions about them. Nature did not wait for understanding. It did not wait for language. It did not wait for certainty. It simply worked, and in doing so, it left behind patterns. Patterns we are still learning to notice, still learning to describe, and still learning to respect. As you rest with this thought, you may find that curiosity no longer feels urgent. It becomes something softer, a quiet companion rather than a demand. The questions are still there, but they no longer need immediate answers. They can drift, like leaves turning slowly toward light, like birds aligning with a planet beneath them, like energy finding its way, not by force, but by fit. And so, we arrive at the end of tonight's exploration. Whether your eyes are still open or already beginning to close, thank you for sharing this quiet journey. Knowledge does not always arrive with clarity, but it can arrive with calm, and sometimes that is enough. Rest gently wherever and however you may be listening.